on vacation at Disneyland this morning, so
Oh, nice.
yeah, so I may have only 15 minutes to spend to ask questions.
The one close by, or I guess the one close by, right?
Yes, yeah,
Okay, good.
Disneyland.
Okay, so let's start then with questions. Which one would you like to start with, homework or the worksheets?
The homework.
Okay.
Let me see. I thought I wrote down.
Okay, let me just grab the blackboard, and then I'll start sharing that. Okay.
Okay.
Okay, so you should see the blackboard now. So homework. Okay, I'm gonna go to homework. Which one, Doppler shift or the black body?
The Doppler shift.
Okay, the other one is harder actually. I think the hardest one is the black body.
Okay, we'll start with that one then.
Whatever you want.
Yeah.
Okay, so black body, fine. So luminosity should be easy. Let's see, black body. Number one, I think it's easy. I'll open it, but that's easy.
Okay. Yes.
So this one, right? This is just basically you have wavelengths on the x-axis, and you just need to rank over here. Where do you get the most energy at what wavelengths? So
right. So I put green, yellow, and blue, indigo, violet, orange, and then red was the
something
least.
like that, exactly. Yeah. Okay, so that's just like reading a graph, okay? And so what would be the color of this object?
Let's see, the color of this object would be green because it has the highest energy output.
Okay, great. Okay, so let's see now the next one. B2, black body 2, okay? You see it?
Yes.
Objects A and B. Okay, fine. So this has a lot of questions, but I think in the homework, what I really care about is whether you get, let's say, from looking at these two, which one has the higher temperature and which one is bigger. Those are kind of the key questions that I ask, because these worksheets, they have like a lot of different questions, but those are the ones that I care about. But so let's say over here, rank the energy output per second. What do you say? How does it go?
For object A, it starts at violet.
Exactly.
And then goes down through red.
Exactly. Okay, and for object B?
It's the opposite.
It's the opposite. Good. Okay, so, okay. I don't know, do you want to go through this C, D, E?
Well, I think they're all pretty obvious.
Pretty obvious, I agree.
Yeah.
I agree. Okay, but the harder ones are now this one. So H, rank the wavelength of peak output of objects A and B. So which one peaks at longer wavelength? Let's go back to the picture. Which one peaks at the longer wavelength?
So that would be object B, because it's showing more red light, which has longer wavelengths.
Excellent. Very good. So usually students confuse this. When they look at this graph, they think this is the wavelength, but it's not. This is just the energy distribution, and you have the whole range of wavelengths over here on the x-axis. So as we can see, object B gives most of the light here at the red wavelength, which is longer than this violet wavelength over here of the object A. Okay, very good. And then which one is hotter?
Object A is hotter because the shorter wavelengths give out more energy.
Yes, very good. So if most of the energy is given at a shorter wavelengths, that means it has the higher temperature, okay? How about surface areas?
Surface area. I think I put the object B had a larger surface area.
Very good. And what's the explanation?
Due to the area underneath the curve.
Now that area underneath the curve, what is that? Is that the surface area of the object, or it's something else?
That is the luminosity.
Very good. And luminosity depends on?
Surface area.
And?
And temperature.
Very good. So now when you look at these two objects, A and B, if you extend this curve of the object B, I guess you could say maybe they have the same luminosity, the same area below the curve, right? Does that make sense?
Yes.
Okay, good. But now you do know that object B is cooler. So in order for the cooler object to have the same luminosity as the hotter one, it needs to be
Larger.
excellent. Excellent. Good. Okay, that's it. That's the first hard one. How about the
Okay.
next hard one?
Okay.
So how was this? Was this easy? The black body radiation?
Yeah, I think this one was easy enough. I mean, it was difficult, but after reviewing, I had to sit with these homeworks and watch the lectures a couple of times.
Okay.
But after you get one, then it kind of makes sense.
Okay, good. Because this is usually hard for students, if not maybe even like the hardest thing. Fine. So this is now the number 3. What do you say about these two objects A?
Okay. So object A, the energy output per second. Oh, by colors. So the most would be blue because it peaks at blue, and then green, yellow, orange, red, and then indigo and violet.
Okay, fine. I'm
Is
not
that
sure.
correct?
Like, yeah, I mean, I don't know. You would need to do like drawings, but I think you're right. Okay.
Yeah.
And then the same is for object B, right?
Right.
Okay.
Yes.
And then this is all trivial, basically. What color do they appear?
Let's see. So object A they would both appear blue.
Very good. Okay. Now the hard questions. Rank the wavelength of peak outputs of objects A and B.
So the longer wavelength would be object B compared to object A.
Why?
Is that correct? Oh, well, maybe not. Are they the same?
Are they the same?
Colors. Well, I think this one I wrote a question on, because, well, they peak at the same color, but object A has more energy output. So does that mean it's a shorter wavelength?
Well, I don't know. Let's see over here. As you said, they're both the same color. They both give you most of their energy at what color when you look over here?
At blue.
At blue. They both give the most. Like if you draw like a line, right? It's go through both peaks. So that means they both basically have the peak energy output at the same color. And that means at the same wavelength, right? I mean,
Right.
That's it. You don't need to complicate. So when you look at this, they both peak at the same wavelength, okay? And so basically, there is nothing over here. You cannot really rank these two, longer, shorter, because they peak at the same wavelength.
Okay.
Okay. Does that make sense?
Yes.
Okay.
Yes, that makes sense.
But you are correct. The object A gives you more like energy at that wavelength. How is that possible?
If it had more surface area.
Exactly. Very good. So what about on the next one? What about their temperatures, A and B?
Well, then object A would be hotter.
Why?
Because it has more surface area.
Well, but surface area and temperature are two completely different things.
They're different.
Right?
Okay. Yeah. So then they would be the same temperature?
Yes, exactly.
Yeah.
It's that simple, right? If they peak at the same wavelength, if they give you most of their energy at the same wavelength, that means they're at the same temperature. Now, that doesn't mean they're at the same luminosity, because if they're different sizes, they're not going to be the same luminosities. And in this case of objects A and B, they are different luminosities, right? The curve A is much taller, so more luminosity, and that's only possible if object A is
larger.
Very good. And I think that's the last question, right? So then the temperatures are the same. The total energy output is different. We already said the taller curve means
more energy.
Yes. From object A, and then which one is bigger?
Object A would be bigger.
Okay, very good. Okay, so that's the hard one, and I think the other two are also hard, kinda. Okay, so B4, here is B4. Okay, how about these two?
Okay, so for object A, obviously it peaks at violet, so then it goes down from there.
Mm-hmm.
And object B peaks at red.
Mm-hmm.
And then I guess it would go the opposite direction,
Mm-hmm.
even though there's more red, right?
Yeah. So what
Okay.
colors do they appear? So
So-
basically, object A gives you more of everything. You can see, right? At every single color, it gives more energy. So that's fine. And then, yeah, this is all easy. So what colors are they?
So object A would appear violet or on the blue.
Bluish. Uh-huh.
Object B would appear red.
Okay, good.
Let's see, but object A would give off more red light per second
Mm-hmm.
than object B. And also object A would give more blue light per second.
Yeah, more of everything.
Right.
Okay.
And then the wavelengths, object B would have a longer wavelength and object A would have a shorter wavelength.
Peaks. Yeah, exactly. So the object B peaks at the longer wavelength because it peaks at red, and object A peaks at violet. Okay, very good. Which one is hotter?
Object A would be hotter.
Very good. And which one gives more energy?
Object A as well gives more energy.
Okay, and how about their surface areas?
Object A has a larger surface area because of the what you said that the area underneath the curve is only luminosity, not surface area, right? But it would be more luminous, so it would have to have a larger surface area.
Are you 100% sure in that?
Well, and it's hotter,
Exactly.
so it would have to be larger.
But do you know that? Are you 100% sure? I agree with
No.
you. It's more luminous. It is hotter. But do you know with certainty, 100%, that it's bigger?
No.
You don't. Because you do know why, that the luminosity is very sensitive to temperature, right? So you don't know if this is like more luminous just because it is hotter, or it's also bigger. You really don't know that. Just looking over here, you could calculate, right? So
Right.
you could calculate, but that's not what this is asking you. So in this case, you need to be smart and you choose that there is not enough information, right?
Okay, yes. I don't think I marked that one because I didn't know for sure. So I guess that would be correct.
Yes, exactly. So as I said, like, you could calculate this using the Stefan Boltzmann's law and like comparing the temperature difference, because I know, let's say over here, violet is approximately 400 nanometers wavelength and this is 700. So I can see that this object is twice as hot, object A than B. So I already know that it's going to have 16 times more luminosity just because of the temperature, right?
Right.
So I don't know, like, you could cut 16 of these little B pieces and glue them over here and then see basically how their areas compare. But that's too complicated. So in this
Yes.
exactly, in this case, you just choose that you don't have enough information. Okay, that was the hard one. And now this one is sometimes also very confusing for students. So what do you say, objects A and B? Which one peaks at the longer wavelength?
Object A would peak at the longer wavelength.
Why?
Because it peaks at violet, I'm sorry, object B would peak at the longer wavelength.
Uh-huh, very good.
It peaks at red, which is the longer wavelength than violet.
And which one is hotter?
Object A would be hotter.
Why?
Because it peaks at a shorter wavelength, which gives off more energy, which makes it hotter.
Exactly, very good. But what immediately do you see about them? Which one gives off more energy overall? Which one has greater luminosity?
Object B.
So what does that tell you?
That object B must be larger.
Very good. And object A is hotter, but what do you see? It's not really...
It's not really luminous.
Exactly, and that means it's not also really...
Really, it's not large.
Exactly. So sometimes I like to think about this one. Like object A, maybe like a sun, basically when it turns like a whiteboard or something like that, very hot, but like small. And object B might be the sun when it goes through the giant phase. So very big, huge object, but kind of on a cooler size. So that's like, how you can think about objects A and B. Okay, very good.
Okay.
So this is a clear case. Object A is hot, but it's not really luminous, so it's very small, while the object B is everything like, opposite from that. Okay, good. So let's see then the Doppler shift. Is that the next one?
Yes.
Was luminosity fine?
I believe so. Luminosity was fine.
This is I think this is the hardest one for luminosity usually. Let's say this one.
The last one?
Yeah.
Okay. Well, let's see. I put the luminosity of the stars from greatest was, let's see, I went by both surface area and temperature. So star D would be the greatest because it has both the greatest. It has, it has a higher temperature, even though it has a smaller surface area.
Mm-hmm. But did you do any calculations, or you were just like?
I was just comparing
the
surface area and temperature.
So you should actually, you should do calculations, but you can just like take 3 over here because they all have thousands. Over here, you can just ignore thousands. So you have 3 over here. Temperature is 3, and then you raise that to the 4th power. So what does that give you? 3 raised to the 4th power.
3 times 3 is 9, times 3 is 27, times 3 is 60.
81.
81. 81. Okay, I was getting there.
That's good. 81, and then times 2, because that's the surface area. So you get around 160, and then you can immediately look at F star. So what do you get over here? 2 raised to the power of 4. That's going to be?
That's going to be, let's see, 2, 4, 16, 32. And then
only 16, I think, right?
2, 4 times 2 is 8. Oh, yes, 16. Sorry.
16, and then times 4, so it's 64. So you can see actually, once again, just because this has 50% higher temperature, star D, it is actually much more luminous, simply because luminosity is way more sensitive to the temperature. So D is the greatest luminosity, and then it's F, and then it's actually really easy to compare, right? Because
right.
now you have these 2 same temperatures, but sizes are different, and then again, 2 same temperatures and sizes are different. So that's simple. Okay. That's good. And let's say, what else? Luminosity, what was about number 4? I think that was pretty simple. Yeah, this is all simple. Okay.
Yeah.
So let's go to the Doppler shift now, if you want.
Yeah. I think the Doppler shift was, the first one's easy enough.
Okay.
The wavelengths coming towards, but let's see, number 2.
Okay, I open number 1. Yes. Okay.
Okay.
So what's the highest frequency?
It would be C, and then A, and then B.
Exactly. Okay, good. That's simple. And then the wavelengths, that's fine. Okay, number 2. Let's see number 2. Okay. Oh, yeah, this one. Fine. Okay.
So the one with the greatest blue shift I put would be E, since it's coming towards the observer.
So E and D are both coming towards the observer. So why did you rank E as actually being more blue shifted than D?
Because of the length of the arrows. So it says that the speed and direction are indicated by the length of the arrows. So E looks like it's coming faster.
Very good.
And then D. And then B would be no shift, since it's moving parallel or
sideways, right?
Sideways, yeah. And then C and then A would have the greatest redshift, moving away at fastest. Okay,
great. Perfect. Okay, and then 3.
Let's see, and then 3. So the largest shift would be star C. And I said that because I noticed the two red lines one was completely off the chart at this point. So that would have the greatest redshift, or the greatest shift overall. And then star B would be next. And then
okay, just a second. In this first case, and I think they do this all the time, Center for Astronomy Education, it doesn't say redshift, blue shift, but it just asks you basically Doppler shift. And so, yeah, so now, like, what you should do is, like, okay, let's say these two lines that you said, like two redshifted lines, and then let's fix our eyes like on this one. So you should extend this like all across, I guess, all of these, right? All of the other ones, and then just like measure how much it shifted. So I think you're right. The most shift you get from the C, because it's completely like off the charts. And then what's the other one?
And then I said B was next because it seemed to shift blue the most.
Yes, that's what I think as well. Okay. And then?
And then star A.
And
then D, and then last would be star E.
Exactly. D, a little bit blue shifted, and E kind of appears that it's not shifted at all, right?
Right.
Okay, good. And then now the speeds of the stars. Is that related to the previous question?
Yes.
Okay,
yes.
so
the greatest shift has the greatest speeds. So B would be moving towards you, where C would be the fastest moving away. So it would go in order: B, and then D, E, A, and then star C.
Okay, excellent, good. Yeah, Doppler shouldn't be hard.
Right.
Okay, good. And this one. Okay, this is the line from the last week, basically, from when the electron goes from the 3, or actually from the second to the third energy level, right? It absorbs the photon of the energy 656. Okay, the red line. And so now what do you have? Instead of being at 656, you get 5 different stars, and the line is shifted basically at these different wavelengths. Okay.
Right.
And so how do you do this now?
I just wrote in the amount of shift there were. Like the first one has -6. So I just ranked those in order.
That's what I would do as well. So -6, and this is positive, whatever.
7, and then 0, and then +1, and -10. So the largest shift would be E at -10, and then B, and then A, D, and C.
Okay, good.
And let's see, the fastest moving toward would be E, and then A, C, D, and then B would be last.
Perfect. Yes, good.
And that was it.
Yeah. Okay. So that's so the worksheets, were they okay, or you didn't have time to do them?
I think I just looked at them and did them in my head.
Okay, good.
Writing on it, and then I took that quiz.
Okay.
Seemed to be okay.
Okay, great. Fine. So so that's it. And I updated actually my lecture. Somebody asked if I can provide all of the answers. So I did that as well just before this Zoom meeting. So that's
okay.
On the Blackboard. Okay. Well then, good job.
Okay, thank you very much.
Okay, enjoy Disneyland, and then I'll see you next time, the morning time.
Okay. Yes, that sounds great. Thank you so much.
You're welcome. Thank you. Bye.
Bye-bye.